Hi everyone, this is Dr. Sandeep, working as Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about the crystal structures and its types. So, what is a crystal structure? So, solid materials, if you want to classify any solid material, one need to know the structure of that material. So based upon the structure, the properties or the characteristics of that solid material are being described. Now, how the arrangement of these crystal structure of the solid material are arranged, so it classifies different types of material. So based upon the crystal structure only, the material are being classified. And now, based upon the intermolecular distance between the atoms in the atomic structure, describes again the physical or mechanical properties. So how the molecules are arranged, how much distance each molecule is having inside the structure of the material will also describe the characteristics of the material. Now, the solid material may be classified according to the regularity with which the atoms or ions are arranged with respect to one another. So based upon the neighborhood of the atoms, how these atoms are arranged internally classifies the types of solid material. That's why the crystal structure is very important in the classification of solid materials. Now, if you see the figure here, you have different atoms which are arranged side by side with some distance. So this is the distance between the two atoms. Now, if you increase the distance during the solidification time, it takes some more time to get into contact. And if you arrange the same atoms nearby the distance, if you are reducing, then it takes very less time to get a solid. You can convert the material into solid within less time. So that's why, depending upon the structure of the atomic structure of the material, we can easily classify the type of or the structure of the material. Now, a crystalline material is one which the atoms are situated in repeating or periodic manner. So what is happening, if you see in this figure, these atoms are arranged in a periodic and at same distance. If you see, observe, at equal distance you have the arrangement of the atoms which are arranged periodically. And even if you see, you can observe the arrangement of these atoms are repeating the same thing, it is being repeating, and at the same time it is arranged periodically. So like that, you can see the crystalline structure. So it should be a repeating or a periodic array of large atomic distances over a large atomic distance. So this distance help us to find out the solidification and liquefaction of any material or the melting and boiling temperatures of any given material. Now, what is happening here? This long range exists such that upon solidification, so this is very important. So generally, how we can tell that yes, this some material will withstand up to what temperature, okay, during any working operation. So based upon the atomic structure only, we can tell that this, suppose this is the material. So this material, if you are giving some heat to this during the working process, so what happens, this material has to withstand about 1000 degrees centigrade. So how can I tell that this metal will withstand up to 1000 degrees centigrade? Means based upon the crystal structure, how is the distance between the two atoms, what is the distance between the two atoms are arranged in the atomic structure. Based upon that, why? Because when you do the solidification process, what happens, slowly the atoms has to come very close. So it's coming close, and finally it will get to bond. Okay, this complete bonding of all the materials will give us a solid material. So that means there should not be any space between the atoms or the molecule inside the material. So then only you'll get this solid structure or solid material. Then you can easily find out that what is the maximum temperature where you can get the solidification or liquefaction. So like that, this atomic structure is very important uh, to classify any material, and it is very important such that you can tell what is the solidification time. And the atoms will position themselves in a repetitive three-dimensional pattern in which each atom bonds to the nearest neighbor atom. So during this process of solidification, what is happening, whatever the atoms are present here, these will try to come closer to the nearest neighborhood of the atoms. So they'll search for which is the nearest. So you have a number of atoms in the solid materials like this at different positions. Now, during the solidification time, all these atoms has to come closer together so that it has a good bonding energy. Now, how this bonding will happen between the atoms means it will search for nearby wherever the atom is there. So, see here in this example, so compared to this distance, this is very, very less. So, it will try to it will try to get a bond between these two atoms rather than these two. So, like that, it will search for different positions where you have the nearby, and it will try to attract the both the different charges and try to get a single bond, so that forms the a solid structure or a solid body. So this is how the atomic structure or the crystalline structure is very, very important to classify any material. Now, where you can find these types of crystal structures and what is the importance means, here we can get in metals all many ceramic materials as well as the polymers. These crystalline structures are very important during the solidification time. So during the solidification time, not only for the metals as well as for the polymers and the ceramics, this atomic structure or the crystalline structure is very important to classify the type of solidification process. And some of the properties of crystalline solid depends upon the crystal structure of the material, the manner which the atoms are arranged. So this is the very important thing. Once if you know the arrangement of the atoms inside the structure of any given material, why? Because this structure will impact on the physical as well as the mechanical properties. That's why this structure arrangement, how these atoms are arranged, so that is very, very important, whether it is arranged periodically in the same distance or some large distance if the atoms are arranged. So based upon the atomic structure, it will impact on the properties of the material. That's why the crystal structure is very, very important to study the crystal structure while selecting any type of material for the given application. Now, there is an extremely large number of different crystal structures, all having a long range of atomic order. So this varies relatively with the simple structure for metals of exceedingly complex one. So what is happening? Whatever the metals we are selecting, so we have an n number of materials. So each material will have its own crystal structure. Starts from the normal crystal structure to the complex crystal structure. So different crystal structures we have. So starting with the normal and to end of the complex structures, okay, there is a lot of change in the properties, lot of change in the physical properties, lot of changes in the mechanical properties as well as the chemical composition. So that's why these crystal structures generally affect on the all the properties of the material. That's why by choosing any material, one needs to know what type of arrangement are there inside the material. So that is very, very important. That's why this crystalline structure is very important in any application while you're selecting any type of material. Now, while describing the crystal structure, what we are trying to do, we are trying to take some atoms that are being in a solid sphere. So by taking a solid sphere, we can easily explain what type of bonding or what type of cubic structure we have. Suppose in this case, if we take a hard sphere model. So we are considering a hard sphere model. In this, what is happening here? This is termed as atomic hard sphere model, in which the sphere represents the neighboring atoms touch one another. So in this case, we can easily see that how the neighboring atoms are being in contact or how the neighboring atoms are being in bonding with each other. We'll see here. So wherever you're getting here, you have some bonding between the atoms here, the neighborhood. Here we have some bonding. Here also we have some bonding. Here also we have some bonding. And everywhere you can see the edges are directly in contact. That means there is some bond, whether it is a covalent bond, metallic bond or ionic bond, any type of bonding will be there inside where you get the contact to the atoms which are very near. So that's why nearby, nearhood contact. So an example of hard sphere model for the atomic arrangement is found in the common elemental. So what are the arrangement of the atoms are there and how it is being contacting. So this is about the bonding of the solid sphere model. So this is called the hard sphere model, where you can visually see how there is a bonding between the atoms which are closely in contact with each other. So generally what is happening here in this particular case, all the atoms are identical, is it not? So what are the atoms we are considering in the solid sphere model? These are identical only. So sometimes the term lattice is used in the context to explain about the crystal structure. So since it is very identical, we can't identify the complete structure of the material. So what we have to do, we have to take some portion from the complete lattice structure. So that is called as a unit cell. So from this solid sphere, what we are trying to do, we are trying to bring out some small element that is called as a unit cell. So this B is called a unit cell. So in this you can see easily how there is a bonding at the each corner of the element. So here you have some bonding, here you have bonding, here all the corners you have the bonding, and again on the face, upper face you have one more bonding here, bottom face, two sides you have, and front and back. So completely you have all the bonding at all the different faces, from starting from the all the corners, 8 corners, and you have the front face, back face, top and bottom, and right and left. So every point you have the bonding. So like that you have to find out where the bonding is there. If you have a good bonding energy, then you'll get a good solid material. So like that you have to select a material which is having a good physical and mechanical properties. Now this is the complete structure of that whole hard sphere. So this is called as aggregate. That is the complete overall structure of that hard sphere what we are taking into picture. Now from this hard sphere, we are taking just a small element which is called as a unit cell. And we are trying to find for the unit cell how many bondings are there, how many atoms are being bonding for that unit cell. Now from that unit cell, we can integrate the overall atomic structure and find out what is the complete bonding in between the atoms in the complete structure. So this is how we will select a small element which is called as a unit cell. So we'll see what is a unit cell in the next coming slides. So this is about the complete lattice structure. So first figure is about the hard sphere unit cell representation. So this is the complete hard sphere unit cell representation, where you can see all the bonding everywhere, wherever the metal is being touching, there you can see the bonding. And the second figure, if we see the reduced sphere of that unit cell. So visualize, to get a clarity in the visualization, we are reducing that hard sphere unit cell into a reduced unit cell, so that you can see all the points where you are getting the bonding. Now this is the figure C, is the complete aggregate of all the atoms. So you're not considering the small element. For the complete aggregate of all the atoms, you're considering in the figure C. So you can see the picture here where you have the complete aggregate of many atoms. Now what is unit cell? So we are talking much about the unit cell. So what is the use of unit cell, and what is the applications of unit cell, and what is the purpose of unit cell? We'll see here. The atomic order in crystalline solids indicate the small group of atoms form a repetitive pattern. So the atomic structure is what? We have a repetitive pattern, is it not? So it has a number of repetitive patterns so that it will form a good atomic structure. Now from this repetitive pattern of atoms, what we are trying to do, it is used for describing the atomic structure, and it is convenient for us to divide these repetitive methods into a small entities. So these small entities are called as a unit cell. You have a number of repetitive. So here if you see in the total aggregate, you have a small unit cell here. Like this you have n number of unit cells. If you observe, like this you have. And here also you have n number of unit cells like this. But you can't find out the total energy or the aggregate energy. So for that, what we are trying to do, we are trying to find only for this small unit in the total aggregate, and after finding we can integrate this unit cell to get the complete atomic structure details. So that is the use of the unit cell. So what is happening here? A unit cell is nothing but to describe the complete structure, crystal structure. We are trying to subdivide or to bring out the small repetitive entities so that you can easily find out the description of that atomic structure. So that is called as a unit cell. So unit cell for most crystal structure are what type of arrangement is that? Parallelepipes or prisms, which is having a three sets of parallel faces. So if you see here, you have one face, two face, and three face. So all these are three parallel faces. If you see front, back, same, top and bottom same, left and right, you have the same faces. That's why it is having a prism of three sets of parallel faces. So that is about the unit cell, which is having a shape of parallel pipes, or the prisms, which is having a three parallel faces, and one is drawn with the aggregate of the sphere. So in this figure, you can see the clear aggregate. From this aggregate, we are taking a small unit cell. So this is the representation of a unit cell. And this unit cell is chosen to represent the symmetry of the crystal structure. So what is the importance of this unit cell means? To find out the uh, symmetry of the crystal structure, these unit cells are very, very useful, and wherein all the atoms, the positions of the crystals may be generated by translation of unit cell integral distances along each of its edges. And thus the unit cell is the basic structural unit or building block for the crystal structure, and defines the crystal structure by virtue of its geometry and all the positions within it. So depending upon the uh, unit cell, we can easily describe the material characteristics and how the arrangements are there in the unit cell. So based upon these arrangements, it is very easy for us to find out the complete structure. We can study the complete structure based upon the geometry of the unit cell as well as the arrangement of the atoms inside the unit cell. So we can easily find out that. And conveniently, it is usually dictates the parallel pipe corners coincide with the center of the heart space. So how it is being bonding, at what places, where whether it is going on the edges or at the centers. So based upon the bonding, where the bonding is there, we can classify different types of cubic structures we will see now. Furthermore, the single unit cell may be chosen for a particular crystal structure. However, we generally use a unit cell which is having the highest level of geometry, which is symmetrical. So that is very, very important. If it is not symmetry, again the complete structure of the material will change. So the unit cell should be a symmetrical thing. And what is space lattice? So space lattice is an array of points showing how particles are arranged at different sites in a three-dimensional spaces. Okay, so the space lattice is nothing but is again it is an arrangement of different types of unit cells. So yeah, if you take a unit cell, if you arrange this unit cell in the three-dimensional space coordinate, so with how you are repeating the same order or not, you have to see here you have a unit cell here, what we have seen in the previous slides. The same way, this unit cell, if you are trying to repeat the same unit cell, and if you are arranging in the three-dimensional thing, then this type of thing is called as a space lattice. So space lattice is an array of points showing how particles, that is the atoms or molecules or ions, are arranged at different sites in a three dimension. So with respect to the XYZ axis, how these atoms are arranged in the space lattice. So that is called about the space lattice arrangement. In this case, again, based upon that arrangement with respect to the three-dimensional coordinates, you have the different types of cubic structures here. So that is called the metallic crystal structures. The atomic bonding in this group of materials is metallic and thus non-directional nature. So what are the atomic bonding we have in this type of metallic crystal structures? These are all the metals which are involving completely is of metallic nature. And three relative simple crystal structures are found for the most common materials, which are face-centered cubic structure, body-centered cubic structure, and hexagonally closed pack cubic structure. So for the most of the materials which is having a metallic crystal structure, will have these three common cubic structures. First one is called as a face-centered cubic structure. So that is about the this is the figure where you have the face centered. We'll discuss slowly about the each cubic structure. Second one is the body centered, and the third one is called the hexagonally closed pack crystal structure. So these are the different types of crystal structures where we commonly find in any type of metallic materials. Now, if you see one by one, the face centered, this is also called as FCC crystal structure, the face centered cubic crystal structure. So, this crystal structure found for many metals which has a unit cell of cubic geometry. So, this type of crystal structure can be found in many of the metals. So, as we discussed, most of the metals will have those three types. So, one of the type is the FCC. So, the metals which is having this type of cubic structure are of having a unit cell which is having a cube geometry. It should have a cube geometry. So with atoms located at each of the corner and center of all the cubes. So what is happening in this? The crystal structure of metallic materials, so which is having a cube geometry, it should have atoms should be located at each corner. So at each corner, if you see, you have all the atoms here, each corner, as well as it has to be at the center of all the cubes. That's why it's called face centered. To the face, you have at exactly at the center, and also all the corners the atoms has to be arranged. So this is how the arrangement of the atoms are present in the FCC cubic structure, and it is aptly called as a face centered or FCC crystal structure. Some of the familiar metals having this crystal structure are copper, aluminum, silver, and gold. So these are the four common metals which we have these types of FCC crystal structures. That is copper, aluminum, silver, and gold. So if we see the complete crystal structure of these four metallic materials, so this type of metals will have the FCC, which is having a cube geometry, and all the corners are in bonding with the atoms, and also at the center of the cube also you have the atom which is arranged. And the if you see again the hard sphere here model for the FCC unit cell. So this is about the hard sphere model. Again, if you see all the corners are being bonded, and at the center you have again. So this is the hard sphere model, and if you see the B, you have a complete unit cell type of model. So to collect a more visualization in the figure B, you will get where are the atoms are arranged, how the atoms are arranged at the corners, and as well as at the center. So this is how you have the FCC arrangement. And again, if you want to calculate the radius, atomic radius here, as well as the cube edge length, so the relation between the length of the cube as well as the atomic radius for the FCC crystal structure. So this is the unit cell for the FCC type of thing. Okay, so for this FCC, the atomic radius, so this is the radius, atomic radius, as well as the cube edge length. So cube edge length. So from this right angle triangle, you have the relation A is equal to 2R into root 2. So this is how you can easily find out what is the relation between the atomic radius as well as the cube edge length. So if you want to find out any cube edge length, you have to use this formula A equal to 2 into R is nothing but the atomic radius into root 2. So with the help of this formula, you can easily find out the relation between the atomic radius as well as the cube edge length. For the FCC crystal structure, each corner atom is shared among 8 unit cells. Is it not? If you see the complete crystal structure of that FCC, what is happening? Each corner of the atom is shared among the 8 unit cells, whereas the face-centered atom belongs to only 2 faces. And therefore, what is happening here? One eighth of each atom, and of the 8 corners. And what is happening at the center? You have 1/2 of each 6. So 1 by 2 into 6 face atoms. Totally 4 whole atoms can be assigned for a unit cell. So if you calculate this, you'll get the complete here 1 and 3. So 1 plus 3 equal to total 4. So by this arrangement, so here what is happening? 1/8 of each of the 8 corners. So 1 by 8 into 8 plus 1/2 one half of each 6 phase atoms into 6. So 2 3 are 6 and 8 8 1 you'll get 1 plus 3 you'll get 4. So totally 4 whole atoms may be assigned to a given unit cell in case of an FCC. So different phases will have different types of atoms which will be arranged at a given unit cell. And this is where only 4 spheres portions are presented with the confined cube. So this will easily tell us where you have the complete bonding and how you're arranging of different phases. So here, here, here. At the same phase also here you'll get upper portion you'll get. Okay, so like this you'll arrange the corners of the atoms. Two other important characteristics of the crystal structure are the coordination number and the atomic packing factor. So you have different things in the FCC also. What is happening? The coordination number as well as the atomic packing factor. So based upon this atomic packing factor and the coordination number, we can easily tell that how the atoms are very close to each other. So what is the solidity of the metal? We can easily tell based upon these two values of coordination number as well as the atomic packing factor. So for metals, each atom has the same number of nearest neighboring or touching atoms with this coordination number, and for FCC coordination number is 12. So for the FCC type of cubic structure, the coordination number is 12. And the atomic packing factor, how to find out the atomic packing factor? So this can be calculated with the help of volume of atoms in a unit cell to the total unit cell volume. So this is how you can easily find out the atomic packing factor. So what is the? It is the ratio between the volume of atoms in a unit cell to the total volume of unit cell. So this is how you can find out. So based upon this atomic packing factor, how much close the atoms are there inside the metal, we can easily tell. So this is the use of the atomic packing factor as well as the coordination number. And if you calculate the atomic packing factor, it is very close, 0.74. So which is the maximum packing factor possible for the spheres which is having the same diameters. And metals typically have relatively large atomic packing factor to maximize the shielding which is provided to free electron cloud. So this is the packing factor. Exactly how this packing is there inside the structure of the metal will be given with the help of the atomic packing factor. So this is the maximum value where you can achieve the for the solid spheres which is having the same diameters. So that is about the phase centered. Now coming to the body centered crystal structure. So another common metallic crystal structure also has a cubic unit cell with atoms located at all 8 corners at a single atom at the cube. So similarly as we have seen for the phase centered, in this case also the same aggregate. If you consider again from this aggregate, you are taking a small unit which is called as a unit cell, and this unit cell we are seeing how the atoms are arranged in the case of the body centered cubic structure. So what is happening here? This is called a body centered cubic structure, a collection of spheres depicting this structure which is shown in the figure. So this is complete aggregate. So where you are collecting, okay, a small unit cell. So figure A and B diagram show the BCC unit cell. So body centered. So this is the body. For this body is centered for the hard sphere. So that's why it is called the body centered cubic structure. And again, if you want to find out the relation between the chord length as well as the radius. So what is happening here? A equal to 4r by root 3. So you have different relations for each type of cubic structure. For the FCC, you have A equal to 2r root 2. And coming to the body centered cubic structure, the relation between the atomic radius as well as the unit cell length is given by A equal to 4r by root 3. So this is how you have different relations for different types of cubic structures. And there is a complete set of things where you can see the first figure represents for the hard sphere unit cell. This is the hard sphere unit cell, and again we are trying to reduce the hard sphere into a single unit cell. And the third one, you can see the complete aggregate of many atoms, how these atoms are arranged. From that, you are taking a small unit cell. And chromium, iron, tungsten, as well as several other metals can be an examples of these types of BCC structure. And 2 atoms associated with each BCC unit cell. Again, how to find out the how many atoms are there? Here we'll see here one equivalent of 1 atom from 8 corners. So from each 8 corners you have a small 1 unit atom which is being bonding, and each of these are shared among the 8 unit cells again, and the single center atom which is wholly contained with the unit cell. So you have a single unit cell at the center, and also you have one equivalent atom at each 8 corners of the unit cell. So this is the arrangement of the BC structure. And in addition to this, what is happening? The center atom positions are equivalent, is it not? If you see the figure, the coordination number for the BC structure is 8, and each center atom has a nearest neighboring and its 8 corner atom. So the coordination number for this is 8, and the coordination number is less for BCC and than FCC. If you compare the coordination number between the BCC and FCC, what is happening? For the coordination number for BCC is less than the FCC. Okay, and you have about 0.68. So there we have 0.74. So 0.68 is lesser value when you compare with the 0.74. So that's why the BCC value, BCC of coordination number, when you compare with the FCC, you have very less. And coming to the third category of the crystal structure, you have the hexagonal closely packed crystal structure. So it is the shape in a hexagon. So for the previous two FCC as well as BCC, we have taken the cube structure thing. Now coming to the third category, that is a hexagonal closely packed crystal structure, we have to consider the shape into a hexagonal shape. So not all metals have unit cells with cubic symmetry. Why? Because most of the metals will have cubic, but all will not have the cubic structure. So some will have the hexagonal type. So those hexagonal type metals, will see what is the coordination number, what is the atomic packing factor, and what is the relation between the atomic radius as well as the chord length. We'll see in this case. Now, the final common metallic crystal structure to be discussed, which has a unit cell which has hexagonal. So this is very important. So based upon the type of geometry, we are trying to differentiate the type of cubic structure. So this figure will show the sphere unit cell of the structure, which is termed as hexagonal closely packed. So in this hexagonal cubic structure, where the atoms are closely packed with each other, that's why it is called as a hexagonally closely packed crystal structure, HCP. And this is an assemble of several HCP unit cells. So again, how we have seen the different unit cells which are closely packed, and from that we are taking a small unit cell. In the same way, here also we have a hexagonally, if you see this, if you drop these lines, you have some hexagonal shape. Okay, so like that you have a number of hexagonal unit cells, but we are taking only a single unit cell to represent the cubic structure. So from this aggregate, again we are taking a small unit cell which is having a hexagonal shape, and if you see all the edges which is having atoms at all the corners, and again at the center, if you see, you have the triangle, three points where we have the atoms which is being bonding. Now the top and bottom faces of the unit cell consists of 6 atoms. So if you see the top face, how many you have? 1, 2, 3, 4, 5 and 6. Similarly at the bottom, if you see 1, 2, 3, 4, 5 and 6. So bottom face you have 6 atoms, and top face you have 6 atoms. So from this regular hexagon which is surrounding with a single atom at the center, and if you see the atom at the center, you have a single. Another plane that provides 3 additional atoms in the unit cell is situated at the top and bottom. Again, if you see at the center of the hexagon, you have 1, 2 and 3. So this is how the arrangement is situated in the hexagonal at the top and bottom planes, and the atoms in this mid plane have again nearest neighbor atoms in both of the adjacent 2 planes. So again, if you see here, you have 2 adjacent atoms in this plane. So totally on the top you have 6, bottom you have 6, at the center you have 2, at the neighboring unit again you have 2. So 6 plus 6, 12 plus 12, 12 plus 2, 14 plus 2, 16. Total 16 atoms we have in this hexagonal plane. So the equivalence of 6 atoms is contained in unit cell. What is happening here? 1/6 of each of the 12 top and bottom face corners. So what is happening here? 1/6 of 12 at bottom face, and top face completely it is of 12, and one half of each center. One half of each center faces having two and of three midplanes of interior. So this is how the arrangement of the atoms are there. So 2, so 2 plus 1 plus 3, 6. So total 6 atoms are contained in each unit cell. So this is how you have to calculate how many atoms are contained in each type of unit cell. So in this case it is hexagonal shape. In the previous cases we have taken the cube and we are trying to find out how many atoms are being coinciding or which is bonding to the corners. Based upon that we are trying to find out the how many atoms are contained in each unit cell. So after that we can easily integrate the total number of unit cells and we can find out the complete structure of the material. In a similar way, if you find out the atomic packing factor of this same for the HCP crystal structure, we have about 1.663. So this is very high when you compare with the other FCC or the BCC crystal structure. So what is happening here? The coordination number and the atomic packing factor for the HCP crystal structure are same as for of the FCC, that is 12 and 0.74 respectively. So this is a good bonding what we have in case of hexagonally packing factor type of materials. And if you see the atomic radii and crystal structure for different types of materials here, so aluminum will have its FCC type of crystal structure and atomic radius is 0.143, and similarly the cadmium will have HCP type of crystal structure and atomic radius is 0.14. Chromium, like that, different types of metals will have different types of cubic structures, and based upon these cubic structures we will have the different values of atomic radius. So this atomic radius will help to find out the coordination number as well as the chord length. So that's why while selecting any material, so depending upon the application you have to select the material, and this material again will reflect on the type of what type of crystal structure we have. So everything is correlated to each other. So that's why the selection of material is very important in any given application based upon the crystal structures. So this is the different values you have. For lead you have FCC type of things, nickel if you have FCC. So though here lead and nickel will have the same type of crystal structure, but if you see the atomic radius value, it is being varying. Why? Because again the arrangement of the atoms may be far or close to each other. So that is the atomic structure. It completely depends upon the atomic structure. The properties are completely depends upon the atomic structure of any given material. Okay. And coming to the references, we have Introduction to Physical Metallurgy by Sidney Havner, and Essential of Material Science Engineering by Donald R., and Material Science and Metallurgy by Kodigiri, and the fourth is the Material Science and Engineering by William Castle. So these are the 4 references book where you can study the different types of crystal structures. What is the purpose of the unit cell? What is the importance of these space lattice and how we are arranging the unit cell in the space lattice based upon the 3-dimensional coordinates, and what are the different types of cubic structures we have, and based upon these cubic structures how these metals are being differentiated with help of the atomic packing factor as well as the coordination number, and what is the purpose and what is the use of these coordination number as well as the atomic packing factor in describing any material properties. So all these things we can get from these references books. Okay, thank you for this session.
Like, share and subscribe. Hit the bell icon for more updates.